Right. So our subject is compiler design. Right. So what is meant by a compiler? A compiler is a program that takes a program written in source language and translate it into an equivalent program in a target language. See, each and every programming language. See, the programming language, what we already know is C, Java, Python, right? So these are different types of programming languages. So each and every programming language will have a compiler, right? See, a compiler is a program. Actually, a compiler is a system software, or we can call it as a program. A compiler is a program that takes a program written in source language. That is, the input for your compiler is a high level programming language, and your compiler translate the high level programming language into its equivalent target language. We also call the target language as a machine language or machine code or relocatable object file, right? So these are different types of names of your target program. See, compiler. Compiler. So, see, this is a simple block diagram of a compiler. Compiler, it takes input as a source program. For example, it is a C compiler for suppose. For suppose it is a C compiler, right? See, what are the inputs that we pass for a compiler? So, the input that we pass for a compiler is high level language. High level language. As we all know that C is a high level programming language, right? C is a high level programming language. When we pass the high level source code as an input to your compiler will give output as a target code or machine code. So that is the first thing. See, whenever we wrote a particular whenever we write some C program, if we execute your C program, right? See, what is the output that we get? So we mainly concentrate on only the output, that is what it displays on your output console, right? We doesn't bother about, see, what is the input that we passed and how it will be compiled and how the output will be generated. We won't much concentrate on that, right? But the in back end, what the thing will happen is, if we write a program in any particular language, right? So the written language, the source code what we are writing, we call it as a high level language. So we have a Java compiler also, JAVAC. So Java C is a Java compiler. So the input for this particular Java programming languages is high level language. That is the source code what we are writing in our Java, and the output is bytecode. Here in C, the output is .exe file. So different compilers will have different type of target programs, as the syntax and the semantics of each and every programming language is different, right? So I think you people know about Python, isn't it? So what type of language Python is? Python is both a compiler as well as interpreter oriented programming language, right? See, but we can call Python is a type of a object oriented programming language also. So which means that in Python also, the output of an each and every program will be in terms of dot class file, which means that it consists of bytecode. Fine. So compiler is a program. We also call it as a system software. A compiler is a system software that takes input as a high level programming language. For example, if we are talking about C compiler, the high level language is C program. If you are talking about Java compiler, the high level language is Java program. If you are talking about Python compiler, the high level language is Python program. Fine, clear? And and your compiler translate the program into equivalent target language, right? Equivalent program or equivalent target language. Here the target language is a type of a file where the conversion of your source code will be done in terms of machine understandable code, right? So this high level program is understandable for you and for me, right? But your machine doesn't understand what you wrote, right? Compiler converts this source program, right? Compiler converts this source program in terms of target program. So this target program is nothing but a machine understandable program. It is nothing but a machine understandable program, right? See, while compiling, there may be a chance of getting errors, isn't it? So we also get some errors while writing your program. So the error messages may be generated for the mistakes what we write in our program, which we call it as syntax or semantic errors, right? So source program is passed, or a high level program is passed as an input for your compiler. It will generate a machine understandable code. In meanwhile, if there are any failures in writing the high level programming language format, so then there may be a chance of getting errors, right? So this is a basic or traditional block diagram of a compiler, right? When we talk about more about your compilers, compiler translates from a source language. As I already said, it is a high level language to a functional equivalent target language. So target language is nothing but a type of a machine independent language, or simply we can call it as a machine understandable language. Compilers of high level programming language are among the large and more complex pieces of software. So each and every programming language has its own compiler. Originally languages included like Fortran and COBOL. So here we have multi-pass compilers. Here we can have multi-pass compilers. See, actually, what the myth we have is each and every programming language will have only one compiler. Actually, what we know is, right, if we talk about C, we know that we have only one particular compiler for C. If we talk about Python or Java, what we think is we have only one compiler, right? So, some programming language will have multiple compilers. We call it as multi-pass compilers. See, I'll give the difference between what is meant by single pass compiler and multi-pass compiler, right? So now, right? So compiler development, which helped in better programming language design actually. So before compiler came into the picture, we have only basic conversion of our programming, right? So whenever compiler came into the picture, so very advantages available for our data, right? So that is high security, high format specific thing, high optimization. So all those things came into the picture. Compiler development helped for our programming language design in such a way that we can mainly concentrate on syntactic analysis, that so how a programming language should be, right? See how a particular statement will be evaluated, how an expression should be, how a loop should be iterated, right? See, all those stuff will be formed whenever compiler came into the picture, right? So commercial compilers are developed by each and every large software group. See, all those things comes under your RISC. See, RISC is nothing but reduced instruction set computer. So what it says is, see, for each and every programming language, so there we have different type of optimization techniques. See, how optimized your programming language is, that much efficient your programming language should be, right? If we have a very less instruction set, or if we have very less syntax in our programming language, we feel very happy, right? So we don't have much syntax, so we don't need to remember much more syntaxes, right? So all those stuff. See, while creating a particular while creating a particular compiler oriented language. So we need to concentrate on reduce instruction set computer. We call it as RISC. See, why we need to study compilers? See, what is the basic advantage of a compiler? So in generally, background information of any good software engineer is he or she should increase his understanding of language semantics. So seeing the machine code generated for um, seeing the machine code generated for a language construct helps understanding a performance issue of for language, teaches good language design. New devices may need device specific language. New business fields may need domain specific language. See, all this study, all these things, which helps us to generate a new compiler. For example, so I'll give a So I'll give an example. See why C came into the picture, why C programming language came into the picture. Actually, Dennis Ritchie intention is not to create a programming language called C. So his main intention is to create a software for consumer electronic device, just like washing machines, for ovens, right? So different type of what of refrigerators, automatic refrigerators, automatic washing machines. See, for that sake, his intention is to create a software for consumer electronic devices, not for programming like C and all. But in meanwhile, we got an idea, why can't we create a programming language so which should follow some sort of semantics, right? See, if you are a very good software engineer, you should write a program with less lines of code and it should give high accuracy. If we are a very good programmer means we should write a program with minimum line of code, right? By using a minimum code, right? See, and we should get a very effective target code. That is, after compiling your minimum written code, so it should generate very effective machine code, right? And it should give very good logical language design, and the code what you wrote should be adaptable for or should be usable for any new devices that we used, right? See, all those stuff uh, will says that we need a compiler. Compiler is a language translator. Compiler is a language translator. For example, if we have a software in our ovens, see, if we keep some food that we should cook in oven, if we directly keep the food and we insert into your oven machine, it will cook directly, or it will ask for some instructions. Obviously, it will ask for instruction how much time we need to cook the food, and at what level we should cook the food, or for how much time we need to bake the food or cook the food, like what it has, right? So there we should give some sort of instruction to the machine to execute the operation or to execute, and it should provide a result. So likewise, for us, a compiler is also a type of a software where we should provide input and it will gives the output. So in meanwhile, it generates a target code, which is nothing but a machine understandable code. See, applications of compiler technology and tools. So processing XML, other to generate document codes, etc. See, and we have different type of processing, domain specific and device specific language. So what I said, so we have different type of languages or compilers available for electronic devices. So we have a separate software for washing machines, we have separate software for ovens, we have separate software for electric cookers, right? Or we have separate software for automatic mixer grinders, right? So likewise, fine. So we have different type of domain specific and device specific languages. So implementing a server that uses a tool such as HTTP or IMAP, so all those things are different type of servers which implements this type of compiler technology. Obviously, we have natural language processing, right? We have a separate compiler for natural language processing, and we also have a different type of hardware description language to translate the given information in terms of schematic circuit, and we have automatic graph layout, which we use with GraphViz. For example, if we want to write, if we want to draw an image in C programming language, likewise, so we need to use a header file called GraphViz, right? And we have extending an existing programming language, which we call it as versions, and we have different type of programming analysis and improvement tools available in today's market. So we can use our compilers and compiler technologies at everywhere, fine. So as we are using a compiler in our mobile, we are using a compiler in our laptop, we are using a compiler in different type of electronic gadgets. See, all these electronic gadgets what we are using now, all iPods, earpods, right, laptops, mobiles, whatever. So every electronic gadget will have its own compiler to execute the task. For example, if we are using our iPods or earpods, right, so the input for that is a signal, right, a Bluetooth signal. What it will take it as an input, and it will produce an output as a music to your ear, right? So there we have a different type of compiler, right? So, and we have different other applications, like we can use this compiler on natural language processing way. So in addition to this, we have different type of information retrieval techniques, and we have different type of pattern recognition techniques, and we are using this parser in our SQL, right? So many software front end and back end technology related compilers. See, all these things are different type of applications what we have actually, right? So now coming towards the main information about your compiler is, your compiler is divided into two parts. Yes, your compiler is divided into two parts. The first part we call it as analysis phase, and second part we call it as synthesis phase, right? So there are, we also call it as two parts or two phases of compiler. So the first phase is analysis phase, and second phase is synthesis phase, right? In analysis phase, an intermediate representation is created from the given source program, right? So later we'll discuss about that. So first I'll show, see what I said. There are two major parts of a compiler, or we can call it as two phases of compiler. First phase is analysis phase, and second phase is synthesis phase. See, totally there are 1, 2, 3, 4, 5, 6. Totally there are 6 phases of compilers, right? Totally there are 6 phases of compilers. See, someone will say there are 7 phases of compilers. Someone will think that, so there may be a 7 phases of compilers, right? First phase we call it as lexical analysis phase. First phase we call it as lexical analysis phase. See, we call this 3 parts as analysis phase, analysis part or analysis phase, and we call remaining 3 phases as synthesis phase. It's called synthesis phase. See, coming towards your phases of compiler, totally there are 6 phases of compiler. First 3 phases we call it as analysis phase, and next 3 phases we call it as synthesis phase. right? See, totally either generally we call it as totally there are 6 phases of compilers. First phase is lexical analyzer, second phase is syntax analyzer, third phase is semantic analyzer, fourth phase is intermediate code generator. Is I audible? Is I audible?
Yes, ma'am.
Is the screen changed?
Yes, ma'am.
Where is the screen?
Major parts of compilers. ఇప్పుడు application of
Now
phase of a
it
compiler.
is phase of compiler, right?
Yes, ma'am.
Right. So there are mainly 7 phases of compiler, where first 3 phases comes under your analysis part, and next 3 phases comes under your synthesis part. Or we can call it as first 3 phases comes under your analysis phase, and next 3 phases comes under your synthesis phase. See, in analysis phase, an intermediate representation is created from the given source program. Fine. See here, lexical analyzer, syntax analyzer, and semantic analyzer are the parts of this analysis phase, right? And in synthesis phase, the equivalent target program is created from the intermediate representation, that is intermediate code generator, and code optimizer are the phases which comes under your synthesis phase. Fine. See, totally there are 6 phases of compiler for lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, code optimizer, and code generator. See, totally these are 6 phases of compiler. So we are dividing our compiler into 2 parts or 2 phases: analysis phase and synthesis phase. First 3 parts of compiler comes under your analysis part, and remaining 3 phases of compiler comes under your synthesis phase. Each phase transforms the source code from one representation into another representation. Fine. So they communicate with error handlers, and they also communicate with symbol table. Okay, right. So once again, I'll show how it will be. See, this is nothing but a phases of compiler. See, totally there are 6 phases of compiler. First one, LA, is nothing but your lexical analyzer. Second phase, which is nothing but SA, is semantic analyzer. Third phase, which is nothing but semantic analyzer. fourth phase, which is nothing but intermediate code generator, and fifth phase, which is nothing but code generator, and your last phase is nothing but code optimizer, right? So these are totally phases of compiler, right? Fine. So all these phases are directly connected to the two different tables. See, first one is symbol table and second one is error handler. So each and every information available at each and every phase is available at your symbol table, and if we have any error generated in each and every phase, that will be handled by error handler. That will be handled by error handler. Fine. So totally there are 6 phases of compiler. Each and every phase information is available at your symbol table, and if there is any chance of generating error at each and every phase, that is available at your error handler, right? So those are your phases of compiler. See, there are totally 6 phases of compiler. Fine. Right. Next one. So first we need to talk about lexical analyzer. First one is lexical analyzer. Second one is syntax analyzer. Third one semantic analyzer. Intermediate code generator, code optimizer, and code generator. So these are 6 different phases, right? So first 3 phases comes under your analysis phase, right? Second 3, next 3 comes under your synthesis phase, right? So now what is meant by lexical analyzer? See here in this particular representation, so lexical analyzer will get input as what? Source program. Lexical analyzer reads the source program character by character and returns the token of the source program. Fine. Lexical analyzer reads the source program character by character and returns the token of source program. Here, a token describes a pattern of characters having same meaning in the source program, such as identifiers, operators, keywords, numbers, delimiters, and so on. For example, here, see, new val is equal to old val plus 12. Here, how it will be divided into tokens, right? So your compiler will read each and every character by character of your source code. For example, if we write like this, means first it will read N, letter E, letter W, letter V, letter L. So it will think, what is this new val? Is it a constant, or is it a number, or is it a keyword? Is it an operator? And finally checks, is it a variable? Right? Is it new val is a variable? So we also call variable as an what? Identifier. See, for the people who already teaches C by me, they right? So new val and compiler will call it as an identifier. Next, equal to. So equal to, we already know it is an assignment operator. So it is a token. See, this is a token number 1 and this is token number 2. Next, old val. Old val is also an identifier. So it's a token number 3. Next, plus is an operator, token number 4. 12 is a number numeric constant. So it is token number 5. See, for evaluating this particular statement, we require how many tokens? We require 5 tokens. We require 5 tokens. So this is an expected question from lexical analyzer in your GATE exam. Fine. So this is an expected question, right? See, putting information about your identifiers into a symbol table. I already said. So in symbol table, see, each and every information available at your each and every phase is recorded in a symbol table or is known to the symbol table. So here it puts information about the identifiers in a place called symbol table. In a place called symbol table. Right. So next one is regular expressions. Regular expression are regular expressions are used to describe the tokens, which we call it as lexical construct. See, what is meant by regular expression? See, regular expression is nothing but language accept by a grammar. We call it as a regular expression. For example, in the above example, new val equal to old val plus 12, it is a regular expression, right? So, regular expression are used for describing the tokens. Fine. So, a deterministic finite state automata can be used in this implementation of lexical analyzer. Here, this deterministic finite state automata, which considers about each and every token available in our expression, right? So, this deterministic finite state automata, which helps us to recognize or which helps us to identify each and every token available in our regular expression. So in our lexical analyzer phase also, so our finite state automata is used for implementing the lexical analyzer. So final information about your lexical analyzer is it takes input as your source program and it gives output as tokens. And second phase is syntax analyzer. A syntax analyzer creates a syntactic structure. Generally, we call it as a parser. See, the thing which I forgot to say is we also called lexical analyzer as a scanner. See, SCANNER, right? We also call lexical analyzer or scanner. Why? Because it will scan each and every token, right? It will scan each and every token, isn't it? So that's why we also call lexical analyzer as a scanner. So the second phase is syntax analyzer. The syntax analyzer creates the syntactic structure. Generally, we call the structure as a tree. What tree we call it as? We call it as a parse tree. The syntax analyzer is also called as parser, where your lexical analyzer is called scanner. The parse tree describes the syntactic structure. For example, see how we draw a syntax tree for this particular expression new val equal to old val plus 12. See here, first we should give preference for what? Equal to operator, equal to. See what we have: left side value, right side value. Left side value is new value, right side value is old value plus 12. So we should add old value plus 12. So this is a general tree. So that will be elaboratedly represented in a parse tree. See what is this? This is an assignment operator, right? See assignment. See what are the things that we should make assignment? Identifier equal to your expression, right? See what is your identifier? My new value equal to, right? So expression, what here consists of? Expression consists of two variables. See what are those two variables? We call it as first one is identifier and second one is number. So the identifier name is old val and the number is 12. So in parse tree, we clearly elaborate the tokens and operators, right? So generally, new val is equal to old val plus 12 is an expression, right? We also call it as an expression or regular expression, right? First, we need to give a syntactic structure for your regular expression. Later, we need to assign values or variables for your expression. See, all your leaf nodes forms your regular expression. See, new val equal to old val plus 12. So in a parse tree, all terminals are at leaves. In parse tree, all terminals. So later I'll explain about what is meant by terminals and non-terminals. All terminals will be either small case representation or operators. All terminals will be small letters and operators. All non-terminals will be capital letters. All inner nodes are non-terminals in the context-free grammar. So later we'll discuss about what is meant by context-free grammar, context-sensitive grammar, regular grammar, and all. Fine. See this inner notes. So this inner notes, right? See, are non-terminal. See, not this expression generally. In generally, all inner notes are non-terminals, and we represent it in context-free grammar. So when coming towards your syntax analyzer, the third phase is syntax analyzer phase. See, what is the input for your lexical analyzer? The input for your lexical analyzer is source code, right? See, the output of your lexical analyzer is tokens. See, what is the input of syntax analyzer? The input of syntax analyzer is tokens, which is generated by your lexical analyzer. What is the output of syntax analyzer? What is the output of syntax analyzer? Parse tree. So the parse tree is the output of syntax analyzer, and now the same parse tree is the input for your semantic analyzer. See, the output of syntax analyzer is parse tree. The output of syntax analyzer is parse tree that will be passed as an input for your semantic analyzer, right? So the syntax of a language is represented by a context-free language or context-free grammar. The syntax of a language is specified by a context-free grammar. For example, so there are different type of syntaxes for each and every programming language. So structure-oriented programming like C has a separate structure when we compared with our object-oriented programming language called Java. The syntax of each and every programming language is different. So obviously the syntax of language specified by each and every programming language, which we call it as context-free grammar. So the rules of context-free grammar are mostly recursive, obviously because the grammar may be ambiguous, right? A syntax analyzer checks whether a given program specifies the rules implied by a context-free grammar or not. See, actually we think that, so if we did anything wrong in writing a statement, which will think that it is a error of syntax, but it doesn't comes under your syntax. It comes under your semantic. It comes under your semantic analyzer phase, right? So we think that syntax error, right? When we write something wrong, see, C equal to A plus B. If we miss it to keep semicolon, we think that it is a syntax error, right? See, but this error will be generated or thrown by your syntax analyzer, because here we have some rule while writing your context-free grammar by specifying that each and every statement should be end with semicolon. If we miss it to keep the semicolon, what it will throw? It will throw an error. So the error thrown by your syntax analyzer, though, that is the error thrown by your syntax analyzer. Fine, right? So the syntax analyzer checks whether a given program satisfies the rules implied by a context-free grammar or not, right? So the syntax analyzer checks whether a given program satisfies the rules implied by a context-free grammar or not. So if it satisfies the syntax analyzer, creates a parse tree, else it won't create a parse tree. So for example, if we use Backus norm form to specify a context-free grammar, then it will be very easy. See, what is your Backus norm form? That is capital C equal to A plus B, right? C equal to D, C equal to 10, right? C equal to A plus B into C plus D. So if the expression is available in this form, then we call it as Backus norm form. See, context-free grammar or syntax analyzer which follows this context-free rules, right? So now we need to know about what is meant by syntax analyzer and how it is varies from your lexical analyzer. See, when we talk about the construction of your syntax analyzer and semantic analyzer, so which construct of a program should be recognized by a lexical analyzer, and which one by syntax analyzer? So both of them do similar things, but the lexical analyzer deals with simple non-recursive construct of a language, while the syntax analyzer deals with recursive construct of a language. That is, your lexical analyzer simply divides your expression in terms of tokens, but where your syntax analyzer deals with the recursive construct of a programming language. It will check the ambiguity. It will remove the ambiguity. Fine, right? So next one, the lexical analyzer simplifies the job of the syntax analyzer by dividing it into tokens. Right? So and the lexical analyzer recognizes the smallest meaningful unit in a source program, which we call it as a tokens, or we also call it as lexemes. The syntax analyzer works on the output given by your lexical analyzer, and then it forms a parse tree, right? And then it forms a tree, right? So the last point what here they says is the syntax analyzer works on the simplest meaningful units, we call it as a tokens in a source program, to recognize a meaningful structure of your programming language. So now there are different type of parsing techniques available in your, see, as we already said, we also called syntax analyzer as a parser. So there are different type of parsing techniques available, right? So depending upon how the parse tree is constructed, so there are different parsing techniques. So there are two parsing techniques are categorized. So first one is top-down parsing and second one is bottom-up parsing. That is evaluating your expression from top to bottom and bottom to up. So which in terms of trees-like structure, evaluating your tree from top to bottom or evaluating your tree from bottom to up. See, when we talk about top-down parsing, right? So construction of parse tree starts at root and proceeds towards your leaf, what I said, right? So when we talk about top-down parsing, starting from the root to the leaves, right? Efficient top-down parsers can be easily constructed by hand, obviously, right? So here we have two types of parsings, that is recursive predictive parsing, non-recursive predictive parsing, or we can call it as LL parsing, left, right? Left parsing. Here LL is left parsing. Later I will discuss about that in more, right? So second one is bottom up parsing. So bottom up parsing, construction of parse tree starts from leaf node and proceeds towards the root node. We call such type of parsing as a bottom up parsing. Normally efficient bottom up parsers are created with the help of software tools, right? When we compare with top-down parsing, bottom-up parsing is very, very efficient, and of course it is a very easiest way for implementation, right? Bottom-up parsing is also known as shift-reduced parsing, and we have different type of preceding techniques available in this. So we have operator precedent parsing. So we have LR parsing techniques. So which is nothing but so simple LR, look ahead LR, canonical LR. So we have different type of LR parsing techniques, right? So in top-down parsing, we have only two, that is recursive predictive parsing and non-recursive predictive parsing. So that is LL parsing. So in bottom-up parsing, we have two, LR parsing. So that is simple LR parsing and look ahead LR parsing and canonical LR parsing. So these are different types of parsing techniques. And coming towards the next phase of compiler is semantic analyzer. See, in this semantic analyzer, which checks the source program for your semantic errors, and collects the type of information for the code generation, right? So this is an intermediate prior to the intermediate phase, right? So this semantic analyzer checks the source program for the semantic errors. For example, type checking is an important part of semantic analyzer. For example, new val is equal to old val plus 2. See, if this is a type of integer, so if this old value is a type of float, then it will check. So this type of evaluation is possible or not. So as we know that we call this type of thing as a type checking, right? Right. So type checking is an important part of a semantic analyzer. So such type of errors will be thrown by our semantic analyzer. Normally, semantic information cannot be represented by a context-free language used in a syntax analyzer, right? So this semantic information will not be represented in our context-free language, right? Context-free grammar used in syntax analysis phase for implementing the semantic rules. So the rules is we call such sort of rules as a syntax directed translations. See the rules for your context-free grammar. The rules for your context-free grammar, we call it as syntax directed translations, right? So this type of identifiers, see here, new val, old val plus 2. So this type of identifier new val must match with the type of an expression old val plus 12, right? See here completely depends upon the data type what we specify, right? So here important thing is type checking will be done by a semantic analyzer. So now up to now we discussed only these three phases of compiler, right? So this three phases of compiler comes under your analysis phase. Okay. So in next class we'll discuss about next three phases of the compiler. Okay.